All right, let's look at the divergence theorem first in a 2D version. All right, so you have a double integral over the region A. You have a divergence of the vector field V, dx dy, is equal to the line integral over the boundary of the region A, and the V, vector field V, dot product with the outer normal vector of the the boundary of A, ds. ds is the arc length element. All right. So let's prove this one. All right. All right. As it turns out, this is just the rewritten version of Green's theorem. So here's the Green's theorem. So let's rewrite that. Right, so if we rewrite this Green's theorem to the left-hand side, so you have a double integral over the region A, so that's easy. Right, so I'm gonna write it as, alright, so you have a partial with respect to x, and we have a partial with respect to y, and so partial with respect to x is applied to q, so we put q here. And partial with respect to y is applied to negative p, so we're going to put negative p there. All right, so we can rewrite it this way. All right, so you can see that here. This is going to be the divergence here. All right, so we can probably write this notation, divergence. All right, then we're going to call this vector field V. Alright, then the right hand side is going to be, so this is going to be a line integral along the boundary of the region A. Right, so since I want to use exactly the same vector field V, so I'm going to put Q comma negative P. Right, then what we want to do is that we want to adjust it. So okay, so Q goes with dy, so I'm going to put the dy here. And then P goes with dx, but there's a negative sign, so I have to put the negative dx. Right? So we can see that the left-hand side is exactly what we want. So it's a double integral over the region A, divergence of the vector field V, dx, dy. Right, so this is equal to, right, so you have line integral over the boundary of A. Then here we have exactly the same vector field V. So we're going to put vector field V. Then we have to interpret this rest of it, so it's vector dy comma negative dx. Right? So if you draw a picture of the region A, so I'm going to just draw a random picture of the region A, which probably might look like that. All right, then so this is A, and the vector dx comma dy would be tangent to this boundary. So here, so if you visualize the vector dx comma dy is going to be a tangent vector, right? But we're interested in dy comma negative dx. So that would be perpendicular to dx comma dy. So this is going to be dy comma negative dx, right? So this vector is always pointing outward and also perpendicular to the boundary of A. So this is always parallel to the outer normal vector. So what we want to do is we want to rewrite this vector as, right, so I'm going to use n, vector n. So this is called the outer normal vector. So here, this is the outer normal because it's perpendicular vector, right? N, right? So dy comma negative dx is parallel to the outer normal vector, and the n has a unit length, so we have to multiply by the length of this vector, which is going to be a square root of, dy squared plus negative, which doesn't really do anything because it gets squared anyway, right? But this is actually exactly the same thing as n times d. This is just the arc length element, so I'm going to use ds. Right, so we can rewrite this guy as, right, so you have a dot product with the outer normal vector. So this is actually a unit outer normal vector. Maybe I should add that. So this is a unit, means that the length is always 1. And then you have ds, right? So we could successfully rewrite Green's theorem as a divergence theorem in 2D. So we got that. All right, then what we want to do next is we want to extend this result to a three-dimensional region. So this is the divergence theorem in 3D. All right, so maybe I should write that. So this is going to be a divergence theorem. So this is a 3D version of it, right? So I'm going to do a little bit of hand waving. So this is how it goes, right? So you have a double integral originally, but we can change that too. So it's going to be a triple integral because it's a three-dimensional, right? And then, so we are talking about the region. So it's a three-dimensional object. So let's say you have x-axis, y-axis, and z-axis like that. And then you have like a floating potato. So this is a three-dimensional solid, right? Then, we're going to call this solid tau, right? So this is going to be an integral, a triple integral over the region tau, right? And we can still define divergence the same way. So divergence of the vector field in 3D, right? Then we have we can do dy, dx, dy, dz. Since I'm lazy, I'm going to use a d tau. Right, so this is just simply, so this is just a volume element. So volume element. Right, so this is the left-hand side, and right-hand side is going to be, so it was a line to go over the boundary, but if you have a solid, the boundary is going to be a surface. So this is going to be a surface integral over the boundary of tau, right? Then, so v is v, right? Then we can define outer normal vector. So you have a solid. You can see that the outer normal vector is just, it's a vector perpendicular to the solid, and it's pointing outward, and it's a unit length. So it looks kind of like that, right? So these are the outer normal vector. So we can define that. So you have an outer normal vector. And then this is, since this is a surface integral, we're going to have a surface area element. So we'd use the d sigma, right? So this guy is the surface area element, right? So that is the more general version of the divergence theorem. So we can do divergence theorem in two-dimensional, which is just a rewritten version of the Green's theorem. And we can extend it to 3D, which is more general divergence theorem here. All right, that's it. I hope that this was clear.